Welcome to the session on conditional probability. The objectives for this session are to understand conditional probability. Depending on the outcome of a previous event, the probability of a subsequent event can change. For instance, if it rains on a particular day, the probability of a family going to the park will change. If A and B are events, conditional probability is probability of B given A equals the probability that B occurs given that A has already occurred, or probability of B given not A equals the probability that B occurs given that A has not occurred. If events A and B are independent, probability of A given B equals the probability of A given not B, which equals the probability of A, and probability of B given A equals probability of B given not A equals the probability of B. This condition can be used to determine independence. A restricted sample space gives the outcome where one event has already occurred. Problems involving conditional probability can be solved using the restricted sample space. Let's now take a look at an example. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at Part A first. Here's the scenario. 350 students are asked about their hobbies. 168 say they play badminton and 231 say they play tennis. Of those who play badminton, 54 also play tennis. We are required to draw a two-way table to show this information. So let's begin. Here's our table. Of course, B represents badminton and B dash represents not playing badminton, and similarly for T for tennis. So let's begin. We have a total of 350 students. Out of these, 168 say they play badminton, so that goes in the badminton total cell. 231 say they play tennis, so that goes in the tennis total cell. Of those who play badminton, 54 also play tennis, so this goes in the cell which crosses badminton with tennis, as shown here. Therefore, we know that 168 minus 54 play badminton but don't play tennis, as shown here. This comes to a total of 114. We can now calculate the tennis and not badminton group. Here, there are a total of 231 students who play tennis, and 54 of these play badminton. Therefore, the rest, in other words, 231 minus 54, don't play badminton. We can also now calculate the total who don't play tennis. In other words, 350 minus 231, which comes to 119. And now we can calculate the total who don't play tennis and don't play badminton either. In other words, 119 minus 114. And finally, the total who don't play badminton is 177 plus 5, which is 182. We can double check this table by checking the total in the other direction, and 168 plus 182 is indeed equal to 350. And now for Part B, we can use the table from Part A in order to calculate these probabilities. So in Part 1, we're required to find the probability of somebody not playing tennis. This is equal to 119 divided by 350, which is equal to 0.34. And now for the probability of somebody not playing badminton and not playing tennis. This is equal to 5 divided by 350, which is equal to 0.014. And in part 3, we're required to find the probability of somebody playing badminton given that they play tennis. This time we're going to use the tennis total only. So we have that this probability equals 54 divided by 231, which is equal to 0.234. And now for part 4. We're required to find the probability that somebody doesn't play tennis given that they play badminton. This time, as you can see, we've used the badminton total, so 114 divided by 168, which equals 0.679. And now for another example, pause the video and have a go. Press play when you're ready to view the solution. Let's take a look at part A first. Two six-sided dice are thrown together and the sum of the numbers is recorded. Draw a sample space showing the possible outcomes. So let's begin. We're going to put the dice 1 possibilities on one side and the dice 2 possibilities on the other, like so. And so we can either throw a 1 and a 6, giving us 7, or a 3 and a 4, giving us 7 again, or a 5 and a 1, giving us a 6 altogether. Now that we have our sample space, we can have a go at part B. Given that at least one of the dice lands on a 5, find the probability that the sum of the two dice is exactly 8, stating one modelling assumption used in your calculations. So this time we're only going to need the row and the column for 5. In other words, this is the total we're going to use. The total number of ways in which the dice lands on a 5 is equal to 11. There are 11 ways of throwing at least one 5. And there are 2 ways in which the sum is exactly 8, given that at least one of the dice lands on a 5. So the probability that the sum equals 8, given that the dice lands on a 5, is equal to 2 out of 11. Now let's state our modelling assumption. The modelling assumptions in our calculations are that all outcomes are equally likely. In other words, both dice are fair. This brings us to the end of this session. If you have understood its contents, you should be able to understand conditional probability. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.